In this video, we're going to talk about another application of vectors. We saw force. In this one, we're going to look at velocity. This problem comes from that Larson worksheet, page 420, number 82. So it says, a jet is flying from Miami to Seattle. The jet's velocity in the air, which we'll call airspeed. This means how fast and the direction the plane would be going if there was no wind at all. So its airspeed is 580 miles per hour, and its bearing is 332 degrees. The wind at the altitude of the plane is blowing from the southwest at 60 miles per hour. So I have a bunch of questions here. We'll start with drawing a figure to represent the problem. So I'm going to first draw an airspeed vector, and I'm going to call that A. So we are 580 miles per hour, and it's got a bearing of 332. Let's think about this bearing thing, because remember, that comes from a compass bearing, that a compass points due north. So we're going to go 332 degrees clockwise from due north. So there's 90, 180, 270. And to get to 332 would be another 62 degrees. So that's going to put our vector somewhere in quadrant 2 here. So I'm going to draw that as a green vector. I'm going to make it fairly long because its length is going to be representing this magnitude, which is 580. Remember the bearing of 332, we said 270 plus 62, so this angle right here is 62. So I'm going to call this our airspeed vector right here. Now the wind speed, I'm going to change and call it blue, and it's got a magnitude of 60, and it's coming from the southwest. So since it's coming from the southwest, we are going to draw it as a vector that is at a 45-degree angle going up here in quadrant 1. And I want the size, the length, since its magnitude is 60, then I'm going to make its length significantly smaller than the airspeed vector, which has a length that's representing that magnitude of 580. And I'm going to call this a 45-degree angle here, and this is our wind speed vector. So this is part A. We've got a picture that is representing the information given in the problem. So let's do now part B. We want to get the velocity of the wind as a vector in component form. So if you remember, the way we write a vector is going to be its magnitude times the cosine of its direction angle, comma, magnitude times the sine of its direction angle. The magnitude of a vector is its speed, so we know that the magnitude of the wind vector is 60. So that's going to get us 60 times the cosine of, and we saw, because we just got this kind of general information, it was coming from the southwest, we're going to take that to mean it's kind of right there in the middle. And so that's going to give us a cosine of 45 degrees. The vertical or y component is going to be the magnitude 60 times the sine of 45 degrees. And you're fine to leave it like that because this is going to need a calculator ultimately anyway, but it's kind of nice too because we know the cosine and sine of 45. It's kind of nice to simplify that and just refresh our memory that the sine and cosine of 45, they're both going to be square root of 2 over 2, which is going to give us a wind vector. I think I'll write it up here a little bit. So a nice form of our wind vector is going to be 30 square root of 2, comma, 30 square root of 2. So we've now done part B. So now we want to get our airspeed vector in component form. So we're going to try this again. Now our magnitude is the speed again. So the magnitude of our airspeed vector is going to be that 580. And we're going to have to think a little bit here about what our direction angle is. So we started with the bearing being 332, and we followed that around and said that this reference angle over here is 62 degrees. Our direction angle has to come from the positive x-axis. So our direction angle theta is going to be 180 minus that 62. So from the bearing of 332, we got a reference angle of 62. To place that into quadrant 2, we're going to call that 118 degrees. So that's going to be 118 degrees there. And the y component is going to be the magnitude 580 times the sine of 118 degrees. That's eventually going to go into our calculator. We don't know that one from memory like we did with the sine and cosine of 45 degrees. So I'm just going to leave that as it is. And we have our velocity vector for the airspeed. Now we want to come up with ground speed. And remember, a ground speed, this is going to be the speed relative to the ground, or you can think of it after the wind has acted on it. So we are pointing our plane in the direction of that green vector, our airspeed. The blue vector, the wind speed, is going to act on that. And so our ground speed is going to be the airspeed plus the wind speed. And so we're going to add those components. So the airspeed, we had a horizontal component or an x component of 580 cosine of 118 plus the wind speed, which was our 30 square root of 2. The y component or vertical component of this vector is going to be the y component of the airspeed, which is 580 times the sine of 118 degrees, plus that y component of our wind speed vector, which is also 30 square root of 2. And again, all this is going into our calculator eventually. Let's get a visual of what this looks like. Remember that a resultant, the sum of two vectors, is what we would get if we take the two vectors that we're adding and use them as sides of a parallelogram. And so the resultant, or the sum of those vectors, is going to be that diagonal. So this is going to be a visual representation of our ground speed vector. It looks like it's going to be a little longer, so it's going to have a greater magnitude than the airspeed, but it's also getting pushed by the wind closer to the y-axis. So, we wanted the speed, I'm sorry, so we're not finished here. So for the speed, that is the magnitude of our ground speed vector. And remember, that is going to be like Pythagorean theorem. We're going to get the square root of, and we're going to get 580 cosine of 118 plus 30 square root of 2 squared, plus the 580 sine of 118 degrees plus 30 square root of 2 also squared. So that's going to have to be entered into your calculator. And I believe if you do that, we will get a speed that is going to be 476.97 miles per hour. That's our magnitude of the ground speed vector. And, oh, no, I'm sorry, that's not right. Is it? Nope, I looked at the wrong one. Sorry about that. Let me fix that. That was a different problem. It should actually, because it should be more than the 580, and it is. I think I got 600.3 miles per hour. Sorry about that. So we have done the speed. Now we want the direction of the jet. So we are looking at our ground speed vector, and we see that that is going to make a triangle, right triangle, a reference triangle with the x-axis, and or you can just remember the formula. We can see that the tangent of theta, that reference angle, is going to be the opposite over the adjacent, which is going to be the y value over the x value of that ground speed vector. So it's going to be messy, but we are going to get that theta is going to be the inverse tangent of that, and you can have to use some parentheses when you put this into your calculator. So we're going to get 580 sine of 118 plus, I'm in trouble with my pen here, plus 30 square root of 2. That's going to all be over 580 cosine of 118, also plus the 30 square root of 2. Now, when you do that, remember we're in quadrant 2, so on your calculator, what you're going to get here is going to be a negative angle. I'm sorry, yeah, right, it's going to be a negative angle, so it's going to be a negative 67.485, or we can say approximately negative 67.5 degrees. But that is an angle down here in quadrant 4. That's the negative 67.5 degrees. What we want is, first of all, can we get our direction angle right here? So that would be, so the direction angle, which I'm going to call theta, not the bearing yet, we're going to come back to that. So theta would be 180 degrees minus 67.5. And so I think that's going to be, what, 112.5, I believe. So I'm going to call that theta. So there's our direction angle. Now we've got to figure out what the bearing is. So let's see if we can figure that out. So this, I'm going to put out of colors here. So this 67.5 degrees here is the same as this 67.5 degrees there. So our bearing, which is going to go, I'm going to use this fancy script B, is going to start at due north and wrap all the way around to that, actually it's going to go all the way to that yellow ground speed vector. So that's going to be 90, 180, 270, 270, so our bearing is going to be 270 plus, we said, 67.5 degrees. So we're going to get a bearing on that ground speed vector of 337.5 degrees. And that's the final question we were trying to answer there. All right, very good.